the problem with technology sometimes. Okay. So here's our 4 objectives. We're going to start off to the right with the t-statistic. So again, I'm not going to read all this word for word. I kind of want you to know it's here, but I'm going to give you kind of a flyby. So we're trying to figure out if the statistic has any meaning or not, or is it really 0? So the computer is always going to crank out a coefficient for you. In other words, when we go back to the data that Excel, it's just a stupid computer, garbage in, garbage out. Notice none of these say 0, right? So the coefficient that it's cranking out says that there's something. But if the variation of that coefficient isn't very good, if there's too much variability in it, then it's really kind of garbage and it's not giving us any meaningful information. And so the t-statistic helps us determine whether the variable is meaningful or not. So here's kind of a red flag. Because it's not greater than 2, perhaps tuition isn't an important variable. Remember, we kind of use that one as an income proxy. And then certainly this one is too low, urban. So it doesn't seem to matter if an urban, if you're in an urban campus or not. So the interpretation is this variable is insignificant. Yes, the computer said minus 0.74, but we're going to treat it as 0. The statistics tell us that you need to treat this as 0 because there's too much variability in it. Any questions on that? Make sense? So this is the idea of significance. And what he does for us here is shows you how that is calculated. So the actual formula is this: the coefficient divided by the standard error of the coefficient. The actual coefficient, 0.08 for price slices, divided by the standard error of the coefficient. The standard error is the computer measuring the distance of how much error there is. It's just kind of the intuition behind it. And so it cranks that out, and that gives us this t-value. And here, he gives you a double check of how that variable was calculated. So I'm going to double click this, and which is a shortcut method of B18 divided by D18. So what he did is he took the actual variables over here and showed how they're related to each other. Right? To calculate the t-statistics, he calculated it. So once I hit return on B18 divided by D18, it's 0.011. That was just straight math, right? We used Excel to do the straight math for it, but that's exactly this number. This is the number that Excel cranked out for us. All we're doing is kind of double checking it with the real math, the real formula. Just to kind of prove to you that this isn't just all hocus pocus, that there is some math behind it. And that's the connection of how it's calculated. So he kind of runs you through that. You can double check some variables. Probably the most important thing is the interpretation. And so we've got the rule of 2 that I mentioned before, which is his last note here on how we get that. For the test, we look at the critical t-value. So based on a normal distribution, so a bell-shaped curve, right? Based on a normal distribution, we can calculate what the t-statistic would be for a significant variable. So we call it the critical t. And let's switch over to the document camera. In your e-text, make this a little bit brighter. We've got the critical values for the t-distribution. And so one of the calculations is degrees of freedom. Have you heard in your basic statistics class, is it better to have a larger sample size or a smaller sample size? Bigger, right? What is kind of the minimum sample size to really have any faith that you've got a large enough sample size? Maybe remember that. So 30. Yeah. So if we get up to 30, that all of a sudden that's kind of a magic number from as long as it was a random sample, remember, so there's importance, there's some of that statistical theory. If it's a random sample of size 30, we start to get a little bit more confident about things. And so this thing shows how once we get to 30, the numbers don't start to change very much on the critical values. And so the larger the sample size, the better. And the degrees of freedom are calculated by the sample size minus the number of independent variables minus the intercept, or minus 1 is the formula that you'll see later. But there's a relationship there. All I remember now is there's a relationship between the sample size, which is the most important thing, and then the number of independent variables that you have in determining the critical value for t. So on a two-tailed test, this is the one we typically use. This is why we get the rule of 2. Look at all these numbers between a sample of degrees of freedom of 13 or even 10 to 13, but we want that size to be 30, 2.04, 2.05, 1.96. Once you give above 2 and you have a decent sized sample, you're kind of golden with this rule of 2. All right? So if we come back to here, our t-statistics are just cranked out for us by Excel. Use that rule of 2, we kind of ignore the sign. The sign just follows the coefficient because how you calculate it is the coefficient divided by the standard error. And so therefore, it's always going to follow the sign of the coefficient. So kind of ignore that. It's really the absolute value of the size of the t-stat. If it's bigger than 2, we're good to go. Okay? That means these variables are significant. Questions? All right. I kind of forgot I was going to do this first, but I didn't. So multivariate regression. We threw in the whole kitchen sink here, right? So these are all the variables now that have been run. Here's all their coefficients, the t-stats. And when we look at estimating, well, how many pieces of pizza are we going to sell? Our y hat, right? We can use the regression in the same way we did with our equation to estimate what that's going to be. And this is it. So the number of pieces of pizza is going to be equal to B17 times B18. Well, what's that? B17 times B18. So the standard error of, I'm sorry, I knew I screwed that up. B17 is the intercept plus B18 times 150. If we were trying to estimate how many pieces we're gonna sell, given a price of $1.50, price of a soft drink of $1, tuition is 20 grand a year, and that's it. So that gives us our A27 is one way, but does do it easier to lead to errors. So we're taking our significant variables and we're estimating how many slices we're going to sell. So that's our equation for our regression is, I'm going to use alphas and betas, but beta 1 times x1 plus beta 2 times x2 plus beta n plus times xn. So if you've got n variables in an equation, right? You've got n variables. This is the intercept, slope for x1, slope for x2, slope for x. Right? We're picking off, here's the slope information. These are the betas, that's the alpha. Right? So there's all the betas. And we're just taking that times the value that we have. So we've got the price of slices expressed in pennies. So we have it as 150. So up in this section, the author gave us the pieces of the puzzle just to kind of break it down. So we've got the intercept, which is just a 1, just for simplicity. That's not really the value. That would be like alpha times something. It's just itself, right? It's the intercept. So he just put in a value 1 there so that our formula went straight. And then we've got 150 is 150 pennies. So the price of a slice is $1.50. And then this to the right of it is that chunk of the equation. Beta 1 times x1. That first chunk is this. And then we highlight B18 times the $1.50. So that's that chunk of it, right? And then he did that for all of the other variables. And figured out each chunk all the way down, and then you just add them together. So this is using Excel. This is using Excel to do exactly what I wrote on the board of how we show it in a formula. Yes?
How could they would have used
That's a good question. I think they threw it in there that I think he didn't want to show that point at this time. I told you I went out of order, and you're spot on, by the way. But he wanted to kind of give the intuition of the prediction, and then put in something for all the variables to just kind of show how it would work for all of them. And then he later goes on. And then after you do that, you come to step 1. That's why I said I kind of screwed up going out of order. But you're right. Okay. Anything else? Okay. So the best guess estimate is saying, given our regression results with these coefficients, if a school was to have a price of $1.50 for the slice, a price of a soda at $1, tuition, whatever your tuition is, a school that had $20,000 worth of tuition, our best guess as to how many slices you're going to sell is 7.5 slices. So that is our prediction that we're making based on our estimation. So the economist is getting paid 6 figures to tell PepsiCo how much KFC chicken they're going to sell in a college market. They're doing this type of thing potentially to do a demand analysis. Should we open up a new store in Ottawa, Kansas? One of the things you're going to look at is this, because is the store viable? You know, what information do we have? Well, boss, in 30 other colleges around the country we collected data on, what we found out is that our best guess for this town that you're looking at opening up one where tuition is $20,000 is you're going to sell 7.5 slices. Okay?
So is there a way to find like the maximum amount of slices?
Yeah, you're jumping down to, that's what makes this fun, is we can now say, well, what if, is it a good idea for us to lower the price of a slice to $1? Law of demand is going to sell more, and our prediction is that you will sell 21 based on this evidence. Now, where this starts to get a little too much of a stretch that a researcher would have to be careful about is that is that within the range of a reasonable change given the data, right? So maybe that's too big of a jump to go from $1.50 to $1. Maybe it's not, but at least question that, whether that's reasonable. Because we could make, the computer's always going to spit something out. Certainly this would not be reasonable, is to drop it down to 10 cents. How many are you going to sell at 0.1, or is that a, oh wait, I need a 1. That's a fraction of, well, this is as good as example as any. This is 0.1 of a penny, 1/10 of a penny. How many are we really going to sell? What's your economic intuition, just general intuition? If Pizza Village has pizza at 0.1 of a penny, 1/10 of a penny is the price. Infinity, right? So they're going to be giving them away, but yet the computer says we're going to sell 21. So we kind of went outside the bounds in that case. So you'd have to be cautious about how much you could do. All right, so same thing with the price of a soft drink. If we raise that to $1.50, the same as the soda, we fall down to 3.4, according to this data. And again, maybe that's too much, but that's what the equation's telling us. Let's see, that's supposed to be 100. There we go. Okay, anything else? All right. So he gives you some trips or things to kind of do on your own and double check. This was the, right here's the activity we basically just did by doing a little scenario analysis. So let's see, let's see, that was 1, that is 2, and now we're on to 3. Confidence intervals. Okay, I'm not going to say too much on this. It kind of comes back to what we just did with how confident are we in the 7.5 slices. So our prediction from our bell curve is that we're going to sell 7.5 slices given that amount, right? The top of the bell tells you your highest probability of that happening is that you're going to get 7.5. But of course, in reality, we're not going to get 7.5. We're going to be wrong. So how much error is there going to be? We can use the data here to calculate a range that we believe it'll fall into. And so for this 95% confidence interval, we're trying to capture that 95%. On a two-tailed test, you've got 2.5% here, 2.5% here. So you got 95% falling in this range. And so what the computer came up with was that our lower bound was 5.3 slices and our upper bound was 9.7, according to the data. And to calculate that, this is the formula. BG is best guess. So my confidence interval is my best guess of 7.5 plus or minus the critical T times the standard error. And in this case, because we're using the 95% confidence interval for the dependent variable, the predicted value, we're using this standard error. So there are 2 standard errors. This is the standard error of the regression, kind of the whole result. And it's important to keep that distinct from the standard error of the coefficient, which is this one. So we kind of use that similar concept, and we can create confidence intervals, which we do, on that estimate. So on the price of slices, did that change anything? Did I screw up something? Wasn't that 0.08? Or maybe with all these variables, it was 0.09. I don't know if anybody remembers, but I just caught that it's 0.09 now. So we'll roll with it. So 0.09 is the estimate. Actually, this is not, this is the regression output, so it shouldn't change. 0.09, and we have this standard error of that coefficient. And it says that our 95% confidence interval is that we believe the statistic ranges between negative 0.11 and negative 0.068. So 0.09 falls into that range. Right? 0.09 is kind of in the middle. So 0.06 at the low end, because it's got that negative sign, so it flipped us around on us, right? But we're applying that same concept for how confident we are what that price range might be. Okay, questions there? All right. So that was confidence intervals. Okay, last concept, and we'll call it a day. You can see I'm burning you out here. Understanding the difference between magnitude and significance. So significance is what we've been hammering on with the T-stat. Like, is this really 0 or is it what it is? The magnitude is the size, and that does matter. Size matters if it's significant. So it's kind of a two-step process. We ignore the magnitude if the variable was insignificant. But if we have a T-stat greater than 2, then the magnitude matters. The size of the coefficient matters. Why? Because that is exactly how we come up with our best guess. This number here of 7.5 was determined in part by the fact that this was 0.092. If that was 0.06, we're going to get a different best guess. Questions on that? So magnitude versus significance. Kind of keep those things straight. It's possible that you can have a magnitude that's a lot higher. So check out urban. 0.09 versus 0.74. This is like 8 times the size of this variable. So if it was significant, that could potentially be a bigger deal, but it's not. We're just treating it as 0 because it's significant. All right. Questions? Enough for a day? I see some exasperated looks out there. Is that just because it's 10 or because this is crazy? This is crazy. This is crazy. All right, we will call it there.